right. So now let's switch to the next talk. If Maxim is here.
Yes. Hi, I'm here.
Hi, Maxim. So for the
Hi.
next talk, so we saw one way of trying to understand like black box models, but with feature importance. But still, it's one of the many ways to understand models and machine learning. But we are still much in the framework where we look at correlation between variables and nonlinear correlations. But still, we may fall in the trap of like correlation is not causation, etc., and which translate in econometrics and finance and etc. In lots of false discoveries, and then poor strategies and things like that. So feature importance is of course one way to look at it, and it's getting more and more like under the highlights. And but another way is to look into causality, which is so far more a niche field, despite there are strong pioneers that have been advocating for it for long, like Judy Apple and things like that. But it's still quite niche, and there are not so many frameworks. So it's quite interesting to host Causalence today, because they are doing some auto ML plus causality. So it would be good to understand a bit more on what they are doing, and since it's a booming startup in Europe, that's great. We can have a bit of time with them to discover cutting edge technology. So with further ado, it's yours, Maxime.
Thank you so much. Just checking, are you able to see my presentation?
It's good for me at least.
Yeah, you see the you don't see the others. I guess I see in front of myself another view, but hopefully you should be able to see this. So great. So thank you very much. Would you prefer me if I answer questions throughout the talk, or would you like me to keep questions to the end?
I think it's up to you, but for less description, maybe people can write in the chat, and then at the end we go through them, but up to you.
Sounds good. Yeah, maybe that's easier, because that way we don't risk getting a little bit, you know, kind of with time, right? This way I can time it a little bit better. So look, I'm really excited to speak today. I really enjoyed the previous talk as well. I missed the first part. So sorry about that, but I was quite. It served really as a great introduction for this. So thank you very much for having me today. It's really great to talk to you all and to show you a different perspective on explainable AI, and also a different perspective on how to basically build models. So it's a bit of a bombastic title, but bear with me, and we will try to, as much as possible, really materialize what it is that we're doing. So just very quickly, a little description about us. So we are based here in London. We're currently a team of 35 people, of whom more than half are PhDs. So we're very quanti, lots of people from finance, but also from other fields as well. Traditional machine learning, also physics and mathematics as well. We are actually hiring quite aggressively right now, and so we're going to add another 25 hires within the next 12 months. We have that already budgeted, and I guess I'd like to kind of point out our investor is IQ Capital, which is a really great supporter of deep technologies, companies. So companies that are trying to do something different, new, kind of bring a new kind of technology to market. So that's what we're doing with causality. And I want to very quickly sort of give you a kind of an introductory motivation for causality. So of course, we're all very aware of how tremendously, the tremendous improvement in machine learning over the past 10 years, largely driven by cool technological advances like the GPUs from NVIDIA and deep learning technology, right? So we have incredible accuracy on ImageNet and ability to really understand images very well. We have great ability to understand NLP as well. We also saw that DeepMind here in London has been doing incredible work. For example, building AIs that can play games, and so they really nailed this problem, right, of playing a game with some set of known rules and kind of beating the world champion here, for example, in Go. So what is common to both of these problems to a certain extent is that they are static, and so we do really well in this kind of world where machine learning gets really difficult is when you have a kind of a dynamic world. And so maybe in this kind of a image world, it would be something like seeing an animal that there's some kind of a strange thing that you've never seen before, right? And in that case, machine learning models tend to act in very strange ways, right? They're not going to, a human would tell you here, well, it's some kind of a strange amalgamation of a cat and a dog, right? But a machine learning algorithm is probably just going to fail and tell you something strange. You'd be very lucky if it gave you a sort of a 50-50 cat dog, right? But you really don't know what it's going to do. And so what we're trying to do here is embed causality into machine learning models in such a way so as to make the machine learning models more human and more understandable and more robust. And this is particularly important in the financial, or economic setting where we're all familiar with this concept of non-stationarity. So I want to explain briefly what that means. So it really has to do with the distributions of your data. So distribution can be stationary, in which case it is constant over time. It is the same over time, or it can be non-stationary, in which case it changes, right? And if you trained your data on a stationary distribution, and if the future is also the same stationary distribution, you have a very good likelihood of traditional machine learning really, working really well in that setting. The challenge is when that changes, right? When the test distribution, or in other words, what happens in the future in the model is different from the training distribution, which is what your model has learned from. And so that's called non-stationarity, and is a huge challenge in this world, and one of the problems that we're trying to address. So essentially, this is another way to put it. The machine learning models are sometimes referred to as curve fitting machines, right? So you're really in a very sophisticated way fitting some kind of a model to what happened in the past, but this may not necessarily generalize to the future. Of course, we also have this problem that that really, we also have this sort of an energy budget that, this is something that has come up quite recently. The kind of human is solving a lot of problems with a much smaller energy budget than for example, some of the most sophisticated NLP models, right? So what's going on here? So it's really interesting, and it's a kind of an example of what people would call in kind of old-fashioned AI would call Moravec's paradox, right? So it's this problem. It's the fact that we've done well on perception problems and on problems that for example, image classification, we've done really well. But some problems such as symbolic understanding of the world, we haven't done as well. And that's sort of that's a bit of a surprise. So we, our perspective as a machine learning company is that the fundamental problem is that traditional methods rely too much on correlations. And if we can solve the problem of inferring causation rather than correlation, then we will do a lot better. And so everything that I'll tell you today will be about this notion of, how do you infer causation rather than correlation? So of course, everyone understands that, but let's understand how do we put that into practice. So, here in this video, you can, this is a kind of a funny example of that, right? Potentially a machine learning model would think that the cat is the one that caused that to happen, right? Here are some examples of where this is a problem, right? So some examples include like, unfairness in hiring, losing money on the market. We also have some other problems. There was a Microsoft bot that went a bit wrong and started tweeting some strange things. Some other, biases in various models. So essentially, to really solve this problem, we need this understanding of cause and effect, as I already said. And we're not the only ones that are saying this. I would say that yes, to a certain extent, causality is a nascent field, but I think it's undergoing a real kind of explosion, and it's really a number of top people in machine learning are really strongly have the belief that this is the kind of the way forward. So Judea Pearl is a pioneer in this field who has built the mathematical formalism that I'll be telling you today about. So the graph frameworks are basically his invention. And there is a number of other people who work in machine learning. So, for example, Yoshua Bengio has been doing a lot of work on causal representation learning. And you can see, for example, Jan LeCun as well, saying that, that causal inference is extremely important. So in fact, he says it's an important way to improve generalization. So generalization is this problem that I mentioned, right? You have some data in the past, you've trained upon it, now you're generalizing to the future, and this future is unknown. It's potentially a different distribution. So generalization is how well are you going to generalize from the distribution that you learned upon to the distribution that you're going to need to infer upon, right? And so this is quite a challenging sort of a problem in general. And so to really solve it in full generality, I want to try to explain that you really need essentially an AGI, right? To solve it in its full generality, right? So I think it's important that we set the expectation straight as well and say that whatever we're doing is around techniques that can help us solve this problem and bring us closer, right? But to solve it in full generality of understanding cause and effect, you would really need a fully, an AGI, right? Or a human. Great. So let's begin and understand what is causality all about. So first problem that we need to understand is confounding. So for example, we might want to understand the population birth rate. So here it is. And we might, in fact, there is one thing that you learn when you do causal kind of, causal inference is that, the association of the statistical association between variables can actually flow via these things that are called backdoor paths. So for instance, there is an association here going from the stork population back via these edges to the number of births. And the reason that is happening is because there is this confounding variable here that's the population growth, over the past, right? So if you now thought that, well, I will just simply predict the number of births via, if I simply correlated the births against the stork population, I would see that they are correlated, in fact, and that's a sort of a funny correlation. But this is not causation, right? And clearly, if we were building, if we were a government that was making a policy on trying to promote, for example, more birds, bringing a bunch of storks wouldn't help, right? So this is an example of something where confounding is actually really confusing, because it's not we are trying to kind of nail down the true causes here and not what is simply correlated. So one way in which we can do this is through, so I suppose maybe this is actually a good point to ask any question, if there are any questions about causal graphs. If not, I'll kind of continue. I think most people will find this quite straightforward. So one question becomes, how, if you want to build a good model, what kind of features should you use in your model? And the answer is, to improve your generalization, you should use true causal drivers in your models as much as possible, because those will generalize better. So clearly, a model where I say, if I fit a model to predict my birds as function of stork population, that might work sometimes, but it will fail in these strange situations where, for whatever reason, you don't have as many storks, but you still have birds, right? Or maybe you have a strange country where you brought in all these storks, but the birds are not changing, right? So what you really want to do is build, if you're really trying to build a smart and relevant model, you want to use features that are in what's called a Markov blanket, or essentially in the set of causal drivers of this variable that you want to do. So another example here is cheese and butter. So if I was interested in predicting the price of butter, I'm much better off using the price of milk as an input rather than the price of cheese, right? And again, that's because the price of milk is the true driver here, but cheese isn't. So first question we want to ask is, can we always infer these kinds of graphs? And sometimes we can, because we have the domain expertise. So if we're working in, say, financial markets, we can maybe estimate some of these graphs based on known literature or on our own beliefs or things like that. But we can also use systematic methods to build these graphs, and that is a field called causal discovery. So causal discovery is a field that will take that develops algorithms that take data that is observational and a set of assumptions, and it will help us build a causal model. This is one way to discover a causal model, right? I want to make a point here that there are a few other ways. You could make an intervention, for example, and that will help you answer, build a graph, right? You can also do a randomized control trial. The problem, of course, is that in most realistic scenarios, you don't have actually the ability to do randomized control trials or interventions, right? For example, in financial markets, you can't do an intervention on the market. You're probably not, you don't have enough money to kind of do that, right? Unless you're a sort of a government. And there might be ethical issues as well, which prevent you from making an intervention or doing a randomized control trial. So what you're kind of stuck with is you have to look at observational data, what has happened in the past, and you need to feed it into an algorithm to sort of try to infer causality from that. And so a number of these algorithms exist out there in the literature. And so one of the things that we do specifically is focus on building kind of state-of-the-art causal discovery algorithms. So let me tell you a little bit about those. The causal discovery methods, they have various restrictive assumptions. So I'll tell you a little bit about them. First of all, a lot of them do not have a full understanding of time series. So that's one problem. There are some that do, but a lot of them don't. Then they assume something called causal sufficiency, which is this assumption that there are that in your data you have all the hidden confounders. So in other words, let's consider the case of the storks and birds. If I had a data set of all of these 4 variables over time, let's say, I should be able to use causal discovery and discover this graph based on a bunch of statistical tests. However, if I don't have population growth here in this data set, it's simply not there. It's not a variable. Some of these algorithms will really struggle. They will not find this hidden confounder because they assume essentially they're known to work only in the cases when there is sufficiency and the confounders are there. The other bit is that these algorithms also assume no regime shifts, so they assume stationary data. And they might assume also, some of these algorithms might assume that there is in a time series setting, there is a very strict kind of ordering of time. So there are no effects that happen within one time point. They also have other problems. For example, they are quite slow. They might be very sensitive to hyperparameters. A lot of them are linear, though you can actually extend them to nonlinearity. And there is also pre-filtering that is sometimes required. So if you're dealing with time series data, you still have to deal with normal time series issues. I haven't covered them in this talk, but there are all these issues such as autocorrelations and general non-stationarity, seasonality, whatever in time series, right? So quite often you have to deal with those as well if you want to apply these methods. So that's what we work on. We've developed a number of methods, and I'll show you a paper that we published recently in URIPS. What we work on are methods that work in a broad set of scenarios that don't depend on the choice of parameters, or they're automatically chosen. So we're a combination of automation and causal discovery. So we do both. And we recently published a paper where we took a lot of the existing techniques and we built a framework for testing them out. And then we evaluated what would happen if we purposefully, actually violate these techniques. The real argument is that, well, in practice, people use, wrong statistical methods all the time, right? Nobody really digs in deep into what are the assumptions of the method before they apply it, right? I'm sure maybe you will agree with me that you may have in the past used an algorithm without actually digging in and understanding what are all the constraints where this algorithm should work, right? So our idea was, well, let's pick realistic data sets, let's violate some of these assumptions and see how these algorithms work. And we also figured out a way how to tune and we identified some ways to tune and hyperparameters on these methods as well. And so you can read that paper if you're interested. It's a sort of a survey of all the state-of-the-art stuff for time series, everything that's public. Okay, so what can you do with this? So we just discussed this question of, if you want a model that generalizes well, you want the inputs of that model to be in the Markov blanket, which is basically the causal drivers in that causal graph. So you don't want things that are simply correlated to you through the flow of statistical association. You want things that are actually causal drivers. And so in this little white paper that we took a bunch of models and we built them using two techniques. So the one is using only the drivers that are in the Markov blanket. The other one is using a more traditional sort of feature selection method. So this would be a basically a correlation-based feature selection method with some clustering. So on the one hand, on the blue, you have correlation methods based on feature clustering, you do a bunch of correlations and then you cluster the features. You pick the top features within each cluster and you use that as the input to your models. The the red represents the models that where you use actual causal drivers coming out of causal discovery. And so what we found in that test, we outperformed on generalization set. So out of sample, we outperformed by 42%. But there's more to it than just that. Causality is not just like, can we get better predictions? I like to think of it as causality is sort of about, sort of extending the number of things that the model can tell you about the problem. So what causal AI can do is it can let you incorporate your domain knowledge into the machine learning model. It can let you evaluate interventions or do some kind of scenario analysis. So I'll take you through a few concrete examples of this. Sometimes, by the way, I just want to introduce one term here. People use the word counterfactual, right? So you're asking the question of what would have happened if this had changed, right? And so a lot of times you might be, for example, in a causal experiment, you have only one choice. You can either give a patient a drug or not give them a drug, right? Maybe you gave them a drug and you measured some effect. Counterfactual is the question: what the effect would have been if you hadn't given them the drug, right? So it's asking the reverse question. And to answer that question, you need to be very careful about the way you build your models. And so we'll talk a little bit more about that. And that's where it gets really important to use these techniques. Here's another way in which you can use causal discovery that is really cool. And it was brought up earlier. You've got loads of data, especially financial markets, but overall you might have loads and loads of data, and it's very hard to figure out what is actually valuable and what is going to generalize into the future. So I'll give you some more concrete kind of papers later, but one big challenge is that if you simply try to scan through the world, you would get into this problem of the babies being born and storks, right? You have this problem of spurious correlation or statistical association or kind of like this backdoor association in causality, right? So the problem that things are really confounded rather than being causal, right? So if you're trying to build a financial, a trading strategy, right? Or some kind of an asset allocation strategy, you might get into this trouble, right? So we applied some of these techniques to scan through data sets, and we found that they are much better at filtering out false positives. So that's because causal discovery is very careful about how it calculates the association. So it's able to really discriminate between, I guess going back to the stork examples, it's able to discriminate between, a statistical association that flows via a backdoor, like storks to birds, versus one that's more direct, like from population growth to birds. So that's very cool use case, and I'll show you one concrete example of this, or a few concrete examples of this. So first is a case of forecasting the LNG price, where if you use traditional kind of selection, you would have picked a bunch of features that turn out not to be very useful. This ends up producing models that generalize better in both sign match and an absolute error. Another is the case of a data set where we took a bunch of macro variables and tried to predict inflation. Once again, if you did it kind of using standard feature selection methods, you end up with a lot more drivers and degraded performance. With causal discovery, you actually ended up with better models. Here's an example that I'll show you quickly on energy as well. So this is a combination of actually causal discovery and AutoML, where we very quickly built some models and found that they outperform traditional seasonal models by quite a lot. So this is a 24-hour electricity demand. Here's another use case where this technology can help. So we managed to build a model that would help save 4% of healthcare costs by predicting patient flow. So potentially this has potential impact of billions in the UK, which is quite impactful. So there are ways in which better improved predictions and applying these techniques can really make a big difference. Here's one that I think is more interesting to this audience, which is the case of asset allocation, right? So here you've got the smart beta ETFs, and so if you look at this paper, they basically say, look, there seems to be evidence of data mining. Basically, the ETFs look really great in back tests, but then after they are posted, they don't perform as much. And so this is a clear evidence of bias being made by the entire community, right? Of basically overfitting to the past, right? And so we tried to understand, okay, can we beat this problem? And we built a model where we actually use some of these techniques and other techniques other than causal discovery as well to produce a trading strategy on fundamental data. And so this strategy actually was compared against two other strategies. One was baseline, which is our state-of-the-art AutoML. Another one is baseline neural network, which is also a fully tuned neural network built with also AutoML. And then the last one is Causal Net, which is our implementation of an algorithm that works on a causal graph. So what you'll see is, we tuned all of these algorithms on validation set, and then we use this technique where we picked the best model that performed on the test set. So what was interesting is that then we had another set which was holdout. That was the future. That was real production. And what we found was that all of these other models underperformed compared to Causal Net. So this is another evidence of how of how causal regularization basically helps. So I'm calling it causal regularization because we're saying the model itself is regularized in a certain way to only take into account causal reality. I think I see a hand here. Any questions, maybe?
Yeah, I would like to ask you, does your causal net uses neural network where you use the causality as a feature extraction, or you don't use neural networks and it's a completely like statistical techniques like regression or more of like simpler techniques?
Sure. Yeah, so that's a great question. So causal net is actually implemented using neural networks, and so I called it causal regularization. And so the way we do this is we build a causal graph, and then we translate that causal graph into a neural network. And what is special about that neural network, and where this talk ties to the previous talk, is that this neural network is explainable, but in a different way. Most explainability approaches go from the point of view where you take an existing model and you try to understand how does it behave on points in the training set, right? So if you think about it, the problem with that approach is that you only really know how the model is behaving on data points that you've observed, right? But you cannot apply causality to new data points by definition, right? Because you don't know what those data points are going to be. Causal net is built in a way that you can that the neural network is actually causally regularized, meaning that the structure of the causal graph and a bunch of also additional metadata that we put into it is embedded into the neural network at a very base level. So you, in fact, no matter what future data points come in, this neural network, you can rest assured that it's going to behave in a manner that is prescribed by this causal graph. So there is no way that if you said, for example, that I'll give you a concrete example here. So in fact, this model was a factor model on fundamental data. So we built factors as latent variables in this graph, and we could embed certain causal relationships, for example, or you could also say assumptions, right? So we could say, well, this model, if the value factor goes up, right? No matter everything else held constant, that has to lead to a future return being improved, right? And so you're able to embed these things. So causal net essentially compiles into a neural network, but the network is cleverly designed such that it enforces these relationships. And so explainability is, I would say, at a different level, right? You're explaining it for all, you know how this model is going to behave. And so from a regulatory perspective, I think this is really valuable. You're not just saying, well, here's how the model has behaved for a bunch of points, right? Using Shapley values or feature importances. You're actually going to say, look, this is how it's going to behave for any point within any conceivable point in the feature space. And so that's what we call causal regularization. The fact that you are regularizing, meaning you're simplifying really the model, right? You're forcing it to apply certain domain expertise rules. It was actually great to hear about hierarchical risk parity as well, because unfortunately, I don't have a better slide here. This was an analysis on a single portfolio where we applied what we called causal hierarchical risk parity. So this is a hierarchical risk parity, but using the causal discovery as a mechanism for instead of correlation, and it led to an improved Sharpe ratio and lower volatility. I thought that was quite cool, and it tied into the previous talk as well. This is another example of purely on P&L, looking at long-short portfolio of stocks. This is strictly a portfolio where you kind of go long on the top 20% and short in the bottom 20. The other case where causal AI really helps, and this approach really works very well, is very small data. So imagine that you have a quarterly time series. How do you handle that sort of stuff? That's very little data, right? And so the answer is to regularize your models as heavily as you can and put a lot of domain expertise into them. And so this is an example of a model. I don't actually know what this is, sorry, but we use this technique quite often. So we build models where on relatively small number of data points. We also use another technique called panels. So we do time series panels where you can effectively multiply your data if you have more than one realization of the process. So those two techniques together let us handle some really small data sets. And I guess this is another example of the same prediction where you saw that the predictions have a lower error and they are closer in variance to reality. So that's really interesting. Now I want to talk about the last part of this, because so far we've been focusing on prediction and how much better it is in predicting. But I wanted to make a point that it's not just about prediction. It's about really understanding the world as a human, right? And so to really understand it, you should make sure that you understand what would happen in a scenario, right? If you perform an intervention or a counterfactual. So if you imagine a neural net, right, it is essentially a bunch of iterated maps, right, or sort of functions applied, right? If you try to do an intervention or a scenario planning, right, the kind of naive approach would be to just take a feature vector and to say, well, look, let me change that feature vector, right? I'm going to make this variable 10% higher, right? What would be the effect of, say, this economic policy? Let me just tweak this number, make it 10% bigger. Then I'm going to feed it back into my neural net and see what the neural net says. The problem with that is that it's really uncontrolled, right? You don't have the ability to truly make sure that's a legitimate question, that you're actually going to get something that is reasonable out of that. The reason there's few reasons for that, right? Key reason is that you don't know what is the causal structure, what that variable really is going to change inside the model. And you may not know also, whether that intervention is even a reasonable intervention. So, for example, if I changed, suppose, if I claim that I want to understand my portfolio returns in a situation where the interest rates are higher, I'm not going to just kind of reduce, make the interest rates bigger and feed those feature vectors into my model. That's kind of risky, right? Because I might not understand how exactly my model works. Moreover, clearly there's some deeper correlations there between interest rates and other factors in the economy, right? So I can't just sort of take one number and multiply it. So to be able to really understand this at a deep level, to answer interventions and counterfactuals, so to explain what's going to happen or what would have happened, I need to have a very concrete structural causal model, right? So this is another example of one of these, causal models that kind of points out what variable drives what other variable. And so this is the kind of the answer that, when you have a model like this, then you can legitimately answer, interventional questions. So when I say legitimate, it means that you can actually believe the counterfactual, the answer to the counterfactual question more than you could in a deep learning network. Moreover, you can do other stuff. You can actually, if you embed, fairness into this model, you can rest assured that it will be fair in any condition, right? You don't have to rely on kind of explainability. We call this, ex ante constraints, right? So you're making these constraints ex ante, right? Before you have seen the future, before you, I guess, kind of traditional explainability, sort of things like SHAP values, right? It's sort of after the fact, right? It's looking at the past. So how could you use this? Well, here's a great example. If you're looking at churn management in a company, churn on its own is not so bad. Churn on its own is churn, right? But what you can figure out is that if you target a specific section of churn, you can increase profits by a lot. So it's not so much about trying to understand how many people will churn. It's about trying to understand, given a certain intervention on the people who are going to churn, which ones of those will react to your intervention in a way that will lead to profits. So, for example, if you are in a case of an insurance company and you know that your customer is going to cancel their car insurance, you might offer them a special deal. If you do it indiscriminately, you're kind of eating up your bottom line, right? But if you do it to the ones that that's going to work, that can actually help. You can tune that to increase your profits, right? So like I said, these counterfactuals, they you need the proper model for that. My point is that I'm of the belief that unless, with the exception of linear models in a deep learning network or something like that, you should be very careful if you try to build a counterfactual, because you simply don't have the the right kind of ability to generalize. So a counterfactual on a proper model that's carefully calibrated for causality can tell you what if, what would have happened if I had done this. And it can also tell you how the future is going to change given a certain change. And so in a kind of a regulatory environment, right, we are of the belief that models should be causal, and they should always, give you the kind of an answer, right? Or a reasonable answer. That you can ex ante sort of understand what that answer is going to be. So just wanted to very quickly show you, this is kind of how our product looks like. You're actually able to run all these experiments through it. I'm not going to bug you now about it, but it's very simple. You can run all these experiments in it, and you can also get a library where you can run it locally on your machine using Python, and it can compile and run on GPUs and do all of that stuff. I also added here a bunch of books here. These are sort of really kind of the starting points for causality in general. So we've got the Book of Why, which is a great reading that's non-technical from April himself. There's also a terrific course that I highly recommend that's free online from Brady Neal, who is Benjo's PhD student and a great person, and the course is really great. And then we've got a couple of other books here as well. One of the people that we recently had join our company is a former professor at KCL, who has actually collaborated quite a lot with Joe Halpern on defining these terms of causality and actual causality. So we're doing quite a lot of cool stuff on that. And we also have a bunch of white papers as well. So that's all I have. Thanks very much. I see that there are some questions in the chat, so I'm happy to answer them now.